detector, you read out about a megabyte when you leave on all the zeros, which makes up 15 petabytes per year. And so you can't do this. I mean, this is the stuff you store with this frequency, right? So you have to reduce to 1 in 10 to the... You want to single out the 1 in 10 to the 7 events that you're actually interested in. So you do this in 2 stages. So there's a so-called first-level trigger. This is built into the detector in custom electronics, FPGAs, those kinds of things. And you want to pipeline, you want to store the information in the detector for about the time that it takes for the stuff to fly through the detector. You don't want to decide just on the inner bits, or you don't want to have to decide whether you throw away the tracking data before stuff has reached the outer muon detector. So you have to store this, and it was decided it's a good idea to store them for 3.2 microseconds, and that means you always store 128 events. And the way this is done is it's pipelined. So you produce the data, and then it's handed through the layers, and while the new stuff is produced in the inner parts, and at the end in the outer parts.
Question?
Yeah.
If this, because of this high collision rate, there are very high requirements for storage and intermediate processing. Why didn't they just inject less bunches so they have less collisions?
Okay, so the question is, why do they use such big collision rates? Well, we want to see the needle in the huge haystack. So, I mean, we need all those to see the interesting stuff. I mean, we're not going to see a Higgs we're not going to see 100 Higgses per second. We have to take data for years with 100 interesting events per second to dig out the interesting information. So in this early custom electronics stage, the event rate is reduced to 100 kilohertz, and then comes the second stage. Here, all 700 so-called front-end electronic modules, which already collect the data of large parts of the detector, are read out, and the events are reconstructed. That is, the tracks are reconstructed, and data from the energy measurements in these calorimeters is brought together with the tracks, and it's determined what kind of particles have flown through the detector. And you want to boil this down to this data reconstruction stage takes about a second per event. So it's distributed on a shelf, on shelf hardware, so order of 1,000 off-the-shelf PCs, each one dealing with one event for a second and deciding whether to keep it or to store it. And now, at this point, ordinary RAM is also fast enough. It wasn't fast enough in the earlier stage. But still, there's the significant problem because you want to bring the data from 700 components of the detector to 1,000 PCs. And you want to switch the data that goes through, and the data rate is 100 gigabytes per second. So you see there's a non-trivial problem to be solved here. And then there are also tags on the event saying, oh, this was an event with 4 muons making all the way to the end of the detector. And you store it in a grid, so the data storage then is on the top of the Earth, and then it's distributed. I mean, not in the basement where there's the detector, but on CERN ground, and then it's distributed to like 100 institutes all over the world, where people then do offline data analysis with the recorded data. And as I said, data production is about 10 terabytes per day, so you can carry around a couple of hard drives every day. Okay, so why do we do this? I mean, this is fundamental research. This is good for nothing. We just do it because we're interested in how nature works at the smallest scales. But we always have to justify ourselves. I mean, it's interesting for us, and hopefully for you, but if people pressure us, especially politicians, we can point to a couple of things. So we also have our Teflon pens. So first of all, I talked about these magnets. And particle physics helped bringing superconducting magnets from something you did in a special purpose low temperature lab to industry scale. So they needed some thousand of these magnets, and they had to produce them at industrial rates. And now companies can produce these magnets at good fault tolerance levels. And this was the time when also when medical industry could purchase these magnets, and you find them now in your local NMR scanner when you have your knee injured or something. You get the magnets from high energy physics. But we have another big business case, and it's this guy. Who recognizes this guy? This one here? It's Tim Berners-Lee. And this was the first HTTP server in the world. And HTTP was invented by particle physicists because they wanted to communicate their physics data with hyperlinks and pictures and everything, and now you know what happened to this. Okay, so HTTP is a spin-off of high-energy physics. Okay, so this was the second part. Now I'm coming to the last part, my own area of expertise, and I couldn't find good pictures on the internet, so I had to draw them myself. So this is... so this is a less than 10-minute introduction to string theory. So first of all, what's string theory? So first we have to talk about general relativity, Einstein's, which is really the theory of gravity that Einstein brought us. And the main message is that space-time itself is not just the stage where physics happens, but it's dynamic. So I tried to draw the Earth, the Earth here and the Sun is curving space-time. So I'm trying to draw, and the Earth feels the gravitational force from the Sun because it feels the curvature of space-time. I mean, this is just a picture. Don't take it too literally. And it makes the Earth go around the Sun rather than straight line. So whenever you have mass or energy or momentum, it curves space, and this is how gravity works. That's in a nutshell general relativity. So this is supposed to be an apple. These are two flies. This is supposed to explain how this works. So I'm a bit short on time, so just a hint. So these two flies argue, and then they decide to walk away from each other, and this one walks away in this direction here. This one walks away in this direction, and they don't want to see each other again, so they walk in a straight line. But because the apple is curved here and there's this thing, it turns out, although they always walk in a straight line, they meet again. Right? And this is how it's the curvature of the surface of the apple, which makes the two flies come together again. But when they look back, they see, oh, there's an attractive force that has actually forced us to come back together again. And that is exactly the same force the Earth feels. When you're at the Earth, you see, oh, there's the Sun in the middle, and there's an attractive force. But actually, no, it's space-time that's curved. Okay, so that as a background. Now imagine we build even bigger particle accelerators. So big, so here is my proton, here's another proton. I throw them together. But now I want to look at so small structures, and I crank up the energy to such a degree that this energy that comes together in the collision is so strong that the gravity of this energy is relevant. And in fact, it curves space and time, and it curves it so much that you produce a black hole. You produce something that curvature is so strong, nothing, not even light, can get out. Right? So I produce a black hole. And that means I try to look at something very small, but I can't see it. Right? Because there's the black hole. Stuff disappeared in the black hole. I can't look at it. And it seems like there's a fundamental limit on how small things I can see. That's very important. So, because when you try to look at smaller things, the curvature of space becomes so strong that it hides these smaller things. So you can even argue that maybe there are no smaller things. It doesn't make sense to ask for smaller things because you cannot look for it. Right? And that is the problem that underlies the theory, the cloud of theories called quantum gravity, because what's important here is you have both quantum physics, which does the particle collisions, and gravity, which makes the black hole at the same time. And whenever you bring quantum physics and gravity together, you cannot avoid this problem. You have something drastic happens. There